You're alive. Okay, so I guess, one of us should monitor the YouTube.
Yeah, you do that here maybe, and I'll just control the camera as needed. So yeah, I guess you really have to do it because I can't be using my laptop for it.
Yeah, that makes sense.
So you run that. Okay.
You're not asking questions.
Yeah, well, I don't think. All right, so I shall do a quick intro. Maybe if we can just there's YouTube with the volume coming through. I think it is, but it's
Hello, testing.
Okay.
Yeah, we're good. Okay. All right. Hello, everyone. Welcome to, was it 528 is our number?
Yes.
Yeah, it's 528. It's great to have you here. We are delighted to have Tree Dow with us today. Mike will tell you more about him in a second. But first, I want to cover some just very quick logistics. So this is being streamed on YouTube as we speak right now. So if you, feel free to ask questions or whatnot, but know that it will come through. What else do I want to say? We're going to have a poll at the end of this in terms of how much we want to do virtual versus in-person things going forward. So please stick around like after Tree finishes for that, just so we can figure out exactly how we want to coordinate this going forward. We want to do the best thing for you. And we're going to try to make this as interactive a session today as possible. So do not be shy. Ask whatever questions you have on the fly. I think Tree has certainly made time for questions at the end, but it's much more fun if we have questions during as well. So with that, any logistic questions regarding the class that I should handle right now? Or yes?
Can we rely on the stream being taught in case we can't make it there?
Yes, you can rely on the stream being up. Maybe we screw up the technology somehow, but in principle, it's supposed to work. So yes.
Yeah, these things, they're technically they're live on YouTube right now, so they should just be online somewhere.
Yeah, they'll be stuck. They'll stick around online afterwards. Other questions? Yes.
Any grading aside from the boards?
Nope. Easy money. Any other questions? Awesome. All right, Michael, you want to intro a Tree?
Yeah.
Take it away.
Today we're very delighted to have Tree Dow, Mr. FlashAttention himself. So Tree is the, what is he right now? He's an incoming assistant professor at Princeton University and currently chief scientist at Decoding AI. He completed his PhD in computer science at Stanford, co-advised by Chris Ray and Stefano Erman. And he works at the intersection of machine learning and systems. His research interests include sequence models with long-range memory and structured matrices. His work has received the ICML 2022 Outstanding Paper Runner-Up Award. So, yeah, very delighted to have you, Tree.
Thank you, Michael. Hi, everyone. Thank you for having me. I'm excited to be here. For this talk or seminar is actually just a bunch of exciting results on at the intersection of machine learning and systems, and some of these results I want to share with you guys. So feel free to stop me and ask questions. It's not a super formal talk or anything. Yeah, so let's get started. So just to motivate, you probably have seen a lot of this. We've seen machine learning making a lot of progress, especially recently. There's been a bunch of tasks that for a while we thought were really, really hard. And now we have machine learning systems that can do these things. So for example, fixing bugs, you could go on ChatGPT or GPT-4 and you paste a snippet of code and you ask it what's wrong, and it'll tell you what's wrong, right? And this is being built into a product like I think Microsoft just released Copilot Pro and things like that. So millions or hundreds of millions of people are using this stuff. But 2-3 years ago, we didn't think these things were possible. Or you can generate art. This is my attempt of using Stable Diffusion. I think this was a while ago. You type in a prompt and you wait a couple seconds and the model does a pretty decent job. I think these models are getting so much better now. in other domains, things like AlphaFold has done such an amazing job at predicting protein structure that now a bunch of companies are using these models to accelerate drug design. And so what we want to ask is, what enabled these advances? What are some of the outstanding problems? And how do you approach these outstanding problems? And so one argument has been that is scale that has brought about quality and capabilities. So maybe some of you have seen this graph where model size and data size have increased about 1,000-fold in the past 5 years or so. So back in 2018 with BERT at 300 million parameters, and last year's Megatron Turing and PaLM at 500 billion parameters, and GPT-4 reportedly at the trillion parameter scale. And as you scale up the model size and you train these models on more data, they just get better. They get better on existing benchmarks, so that's great. But what's really amazing is that they seem to have new capabilities. So here's my attempt of using language models to explain jokes. Let me move this. So I tried 10,000 random restarts of my neural network, but I was accused of overfitting. I guess no good seed goes unpunished. Right? And then I asked a 1 billion parameter model to explain this joke, and it didn't get the joke. It just, when you asked it to explain the joke, it just tried to repeat the punchline without understanding the joke. But if you ask a 175 billion parameter model, it does understand the joke. It does understand this is a pun on no good deed goes unpunished. So this is amazing. It seems like scale is now more closely tied to advances in machine learning than ever before. And with scale, there comes a core challenge, efficiency. And I assume throughout the seminar, you see this issue being brought up a lot, which is efficiency. And there are a couple of reasons why you care about efficiency. One is that efficiency can make training and deployment so much easier, and it can facilitate research. So right now we have a bunch of large and slow models that do really well and they're really accurate. Can we get to the point where we have smaller and faster models that do just as well? And we've seen a lot of progress, especially in the last year or so, where now we have 7B models doing as well as 70B models. We have models running on phones that are super capable. I think, for example, Stability just released like stable code that's like 3B that's run on phone, that's about as good as some of the larger code llama models. So we've seen amazing progress here. Another reason you might care, these are very practical reasons to care about efficiency. Another reason you might care about efficiency is that efficiency can unlock new capabilities. So here's an example from, I think, this is GPT-3 Playground, so that was last year. When if you ask it to write a 4,000-word essay on the best ice cream flavor, it couldn't do so. This was last year. This was GPT-3. And now GPT 3.5 can deal with 16K contexts, thanks to some of the work that we've been doing and the community have been doing. GPT-4 can scale to 128K contexts and so on. So this is amazing. And I'll argue that some of these advances are due to better efficiency. I'll touch on this due to some of the work that I'll touch on. Yeah, so efficiency, you might care about it from a practical point of view, make it easy to train and deploy models. From a capability point of view, I think efficiency can unlock new capabilities as well, and I'll touch on this. So my approach to understanding efficiency is to understand both the algorithms and the systems side. So on the algorithm, you can spend a bunch of time understanding things like matrix vector multiply, which is kind of the fundamental operation in a lot of these neural networks. Or you can try and understand the attention mechanism, which is kind of the heart of the transformer architecture that has brought about a lot of these advances. On the system side, we want to understand things like hardware accelerators and distributed systems. Basically, whatever these models are running on, right? So things like GPUs, you want to understand these are block-oriented devices, and that has a bunch of implications on how you should design your model, how you should design your algorithms. And when you wire a bunch of these accelerators together, you want to understand that these have asymmetric memory hierarchy, and you can exploit that to make your system, 5 to 10x more efficient. And I'll talk about some of the ideas of how to do that. So as an example of how we can think about both the algorithm and the hardware. So I'll talk about one main idea, which is hardware-aware algorithm. So any kind of algorithm that takes advantage of the hardware that they run on. So for this talk, I'll mention two examples of this idea. One is I/O awareness, which is you want to, for example, for GPU memory, you want to reduce the amount of reads and writes to GPU memory because that really slows you down. And that can bring you significant speed ups. So an example is FlashAttention. So this is joint work with Dan Fu and Stefano and Atri and Chris, who are at some of them are at Stanford. So this is a fast and memory efficient attention algorithm with no approximation. And that's the first half of the talk. For the second half of the talk, I'll talk about some of the how some of these ideas apply to new model architectures, not just transformer, but these ideas are more general, and we'll show how they apply to state space model. So I'll show some example of how you can expand the recurrent state. This is a recurrent neural network architecture. We can expand recurrent states into SRAM to avoid memory costs, and this leads to Mamba, which is a joint work with Albert Gu, who's now he's a professor at CMU. So there's a selective state space model that the exciting thing is that it's not a transformer, but it matches transformer on language model with a much faster inference and much longer context. So I'll touch on some of these points. And we've been very lucky to have some research being adopted by folks in the community. So for example, FlashAttention is now has been part of PyTorch for a while. So I think it's called scale.product attention. So you can call it directly from PyTorch. The folks at OpenAI really like this, so they re-implemented it in the language OpenAI Triton. Folks at Meta, NVIDIA, Microsoft, and a bunch of companies have been using FlashAttention for training and inference. So I think in Hugging Face has also been integrating FlashAttention into some of these models as well. Yeah, so that's kind of the overview of what I'm going to talk about. So for the first half, I'll talk about FlashAttention. The main idea is you want to reduce memory reads and writes. And in the second half, I'll talk about how some of these ideas apply to other kinds of models, such as state space models. So I'll pause here to see if there are questions on kind of the motivation and the overview. All right, so let's get started on the first half of the talk. So I'll focus on this layer, the attention layer, which is this core primitive in the transformer architecture that's being used everywhere. We want to understand what the bottlenecks are, since the bottlenecks are memory reads and writes. We want to understand some of the approaches to reduce this bottleneck, so tiling and recomputation. And I'll show some applications, how this allows you to train transformers faster or with longer context or with better quality. So the motivation why we want to do this is that we want to model long sequences. This is motivation on kind of the AI side, capability side. So one anchoring application is in, of course, natural language processing. I think a lot of you are familiar with, where we need large context to process things like books and plays and instruction manuals and code bases. One example, one thing I really like from, for example, the GPT-4 demo is they just put in like a whole, 50 pages of documentation of a new library, and the model kind of figures out how to use the new library because it can process 50 pages or 100 pages of documents. So these are new capabilities that can be unlocked if the models can process long context. In computer vision, we want to close the reality gap, and we've seen a lot of this in, for example, diffusion models for image generation, where we know that modeling images at high resolution generally leads to better and more robust insight. But if you're using something like vision transformer, which is what most people use, or a diffusion model, high resolution tends to lead to longer sequences. And that just means it's a little bit harder for on the system side or on the efficiency side to deal with high resolution images. So those are pretty popular application domains. But in other domains, I would argue that if you can model long sequences, you can unlock a bunch of new areas. So things like stamp series, audio, video, medical imaging, where data is naturally modeled as sequences of up to millions of steps. One example is histopathology, where we have some folks from Chris Ray's lab who study these kind of cell images where they're trying to predict things like cancer tumor and things like that, where you need very high resolution, and people don't ever downscale these images. So the images are so high resolution that when you vision transformer, you can't deal with like a million time step. So that's just a motivation of some of the applications that can benefit from modeling long sequences. So why can't we just, what is the problem of modeling long sequences? And I would argue that efficiency is one of the main problem, is one of the bottlenecks for modeling long sequences, especially with transformer, which is the dominant architecture right now. So here, in terms of terminology, I will use context length to mean how many other elements in the sequence does the current element interact with. As you increase the context length, you can slow down, or training might completely stop. And I'll give some examples to illustrate. So I'm showing here a plot of the training speed of two models. One is a 1B model and one is a 3B model. And I'm using Megatron LM, which is kind of a state-of-the-art library for training these language models. So this is from NVIDIA. It's been used to train models of up to, I think, 500 billion parameters. So this is kind of a state-of-the-art library. And if you use context length of 2000, that means you're processing maximum a document of 2000 tokens. Then your training speed here, I'm plotting on A100, is pretty reasonable. It doesn't matter what the absolute scale kind of is proportional to how many tokens you can process per second. Higher is better. So, in absolute term, these are very reasonable processing speed. But as you increase the context length just from 2K to 8K, what happens is that your training slows down. For the 1B model, it slows down by 2x. And for the 3B model, you go out of memory and you can't train at all. Right. So this makes sense because now the sequence is longer, so each element has to interact with way more, way too many elements. So you slow down because you need to process, you do more floating point operations. And two, you might go out of memory because you just need more memory to store the longer sequences. And I'll go into the specifics of how. So it's not trivial to just increase the context length. And this has been a problem ever since kind of Transformer came out in 2017. And attention was already a thing before that as well. So it's been lots and lots of paper working on this. So just in terms of terminology, I'll go over just a recap of what the transformer architecture looks like. I know a lot of you are familiar with this. It's just so that we're on the same page in terms of terminology. So transformer architecture is a neural network architecture consisting of a bunch of blocks. Each block is called an encoder block or sometimes decoder block. And each block has two main layers. There is the attention layer, and there is the MLP layer, multi-layer perceptron. So I'll focus on the attention layer because for the MLP layer, scaling up to sequence length is relatively straightforward, but the attention is more difficult. So I'll just go over a little bit of background on attention, just so that the notation, we're on the same page in terms of notation. Okay, so here's what a single head attention look like. So you have inputs, the query and the key, and these are of shape n by d, where n is the sequence length. So as I mentioned, the sequence length is on the order of thousands. And the d is the head dimension, usually on the order of around 100. So given the query and the key, you multiply them together to get the similarity score. So you're essentially doing a pairwise comparison between the query and the key. So every pair of query and key, you compute some score that says how similar they are. And then you normalize them using this operation called softmax. Softmax of a vector just means you exponentiate the vector and divide by the sum so that everything is positive and sum to 1. So it looks like a probability distribution. And as you do this normalization per row, and once you have this normalization matrix A, you multiply by the value, which is also an input, value of size n by d, and you get the output n by d. So written more compactly, output is equal to softmax of q times k, and then multiplied by v. So this is actually a very, written in this way, it's relatively simple. You can write it in a couple of lines of PyTorch, but it is the core, is the heart of the transformer architecture. So we see that attention scales quadratically in sequence length n. This is the core of the problem. So as you increase the sequence length n, you're doing, let's say you double the sequence length n, then that means you have 4x more, 4x the number of pairs you need to do this pairwise comparison. So doubling the sequence length means you increase the amount of computation by 4x and you increase the amount of memory by 4x. So this is why it's hard to scale to longer sequences with attention. So ever since Transformer came out in 2017 and became widely popular, there's been lots and lots of work on approximating attention or trying to scale it to longer sequences. So there's probably, I don't know, 10 papers every week on this stuff, and a lot of them are pretty cool. So I personally have worked in this area as well. So just a little bit of context on how these methods work. The goal here is to trade off quality for speed. So we're going to approximate attention. We say, well, attention by itself scales quadratically in sequence length n. It's too computationally expensive. Can we approximate it? We do less computation or use less memory. The quality might be worse, but maybe there's an okay trade-off. And there are two main classes of approach. One is sparsity and one is using low rank. So on the sparsity side, the core idea is you say, well, attention, instead of doing all this, n square number of pairwise comparison, we'll just decide to ignore some of them, and we'll only do pairwise comparison for some of the pairs. So here in the diagram, I'm showing the cells in purple to denote, let's say you decide some of these cells I want to compute, and some of these other cells I want to pretend that they're 0. I'm going to ignore some of the pairwise comparison. And so if you use this kind of sparsity, then you can do less computation and hopefully get some speed up or memory saving. So that's the idea of sparsity. There are many, many ways to choose which entries to compute and which entries to ignore. So that's why there are tons of papers on how to choose this, either statically or dynamically and so on. So that's one class of methods. The other class of method is assuming some low rank structure on the attention matrix. So you say attention matrix, even though it's n by n, maybe we can assume that it's actually low rank or close to low rank, and then if you can factor it out as two low product of two matrices that are together low rank, then you can do the multiplication the other way, which is multiply by k times v first, and then multiply by q. And then different methods would have different ways to approximate, do this low rank approximation. So the goal here is to trade off quality for speed. And I've worked on this as well. And there's an excellent paper, excellent survey called Long Range Arena, which benchmarks a lot of these efficient transformer methods. Turns out, when after I worked on this for a while, we went and talked to some of the practitioners who train large scale models, and I asked them, hey, do you use these this method or that method and so on? And generally they say no. They say no, we don't really use these methods. And one of the core reasons is that Well, the two reasons. One, first of all, the quality is worse. So, okay, that makes sense. We're approximating attention. We're not computing all the entries. So yeah, okay, maybe the quality is worse. But more importantly, they're not even faster, or they don't even save memory for a lot of them. So this was surprising to me. My mindset was more on the theoretical side. Hey, if you're doing fewer operations, makes sense. It should be faster. Turns out in practice, these are not generally faster. So the core idea is they're doing fewer floating point operations, but that might not necessarily be the bottleneck. So fewer floating point operations might not translate to faster walk clock time. And faster walk clock time is actually what people really care about. So we asked the question, is there a fast, memory efficient, and exact attention algorithm? So I'll show at least one way to get there. But before we get there, we want to understand what the bottlenecks are. Previously, I had assumed that the bottleneck was, we have to do a bunch of floating point operations. So if we can reduce that, we should be faster. But from talking to some of the systems folks, this is kind of the biggest bang for your buck. Kind of the advice they gave me was, did you profile your code? This was a surprise to me because I'm more on the, I came from a machine learning background or math background. So I'm like, hey, I proved this thing, I approximate this, it should go faster. Right? When we talk to systems folks, they're like, did you profile your code? Where is the bottleneck? Right? And turns out if you profile your code on GPUs, the bottleneck is in memory reads and writes. So as I mentioned, we have these large matrices n by n that store the kind of pairwise similarity between the query and the key. And turns out they're just reading and writing these large matrices take most of the time. It's not that the time is not being spent on floating point operation, which are useful. The time is just reading and writing to memory. So this was a surprise, but in hindsight, that kind of makes sense. Yeah, the biggest cost is in moving the bits. Turns out standard implementation requires repeated reads and writes to GPU memory, and that's causing the slowdown. So in order to tackle this problem, we need to understand the hardware just a little bit. So I'll just have one slide, kind of crash course on how GPUs work. So here I'm showing a diagram of a streaming multiprocessor, which is, you can think of as one part of a GPU. GPU you can think of as having 100 of these things. The green box is HBM, or high bandwidth memory. This is what you think of as GPU memory. So if you're using a GPU, you type NVIDIA SMI, and it shows you, I don't know, 24 gigs, 40 gigs, 80 gigs. So that's the HBM. That's a high bandwidth memory. But there are other components, such as the compute units. So these are specialized hardware units that actually does the computation, things like matrix multiply, adding things, multiplying things. And then there is, so that I'm showing that in purple. And then there's SRAM, which you can think of as cache. I'm showing here in orange. So SRAM sits very close to the compute unit. It acts like a cache. Is quite small, but is quite a bit faster than HBM. So this is on the A100, where the HBM, which is, in absolute term is a marvel of technology. It's in absolute term is actually really fast, 1.5 terabytes per second. H100 now is quite a bit faster than that. And it's quite large, 40 gigs, 80 gigs. The SRAM is an order of magnitude faster than that, but 3 orders of magnitude smaller. So you see this kind of memory hierarchy popping up everywhere in computer science. On CPU you have the DRAM and the CPU L1, L2 cache. So here in the GPU you kind of have the same situation, and it makes sense. It comes down to physics. So if you have a compute unit that's built using silicon, there's only so much area around it that you can put silicon to as SRAM, right? So there's limited amount of area that you can build around it that's very close to the compute unit. So that part is fast, but there's not much area. And then as you go further and further away from the compute unit, you have more space to put silicon for the HBM, but it's sitting physically further away from the compute unit. So it's going to take some time to move the data. So this all comes down to physics. Okay, so how does the GPU work? The inputs start out in HBM, also known as the GPU memory. And then you need to move the inputs to the compute unit and SRAM for computation. So there's a data transfer, and then the computation happens. And then you move the output back to write to HBM. So if you want to understand, this is kind of a crash course on how GPU work. Other accelerators are similar. And if you're interested, I highly recommend this blog post by Horace He. He's a PyTorch developer. He wrote an excellent blog post called Making Deep Learning Go Brr from First Principles. So I think it's, you spend 10, 15 minutes reading the blog post, and like you understand kind of machine learning performance way more. I think it's one of the highest bang for your buck thing to do, is to read his blog posts. So now that we understand the hardware a little bit, we ask, can we exploit the memory asymmetry to get speed up? Now that we understand there's HBM, there's SRAM. So the trick is I/O awareness, which is we're gonna try and reduce the reads and writes to HBM and do a lot of reads and writes to SRAM. So that's the core idea. Once you understand kind of the bottlenecks, once you understand the hardware model, then the approaches don't look so alien. The approaches kind of turn out to be quite natural. So that's a little bit of background on attention and hardware and where the bottlenecks are. So I'll pause here to see if there are questions. Yeah.
So I have a question, which is, I mean, the tricks that go into FlashAttention and, profiling code, like, these are like fairly standard performance engineering tricks. Like, why, in your opinion, did no one at NVIDIA like bother to profile the attention code and, figure this stuff out?
Right. Yeah, that's a great question. So, Transformer came out in 2017, and kind of lots of people switch over, and attention performance is or speed is one of the core problem. So folks at NVIDIA and Microsoft and so on have certainly optimized attention. They spend a great deal of engineering effort optimizing attention. I'll go into some of the issues there. The issue was that I think they were thinking of it from a like kind of more purely hardware perspective, where they think of well, I need to do a softmax, and I can kind of fuse it with the next operation. Sometimes there's like causal masking, so people have done things like fusing softmax and causal masking and so on. But they weren't thinking about it from a kind of mathematical perspective, which is, I'll show you, you kind of need this mathematical trick of softmax rescaling in order to make the algorithm work. So I think if you just approach it purely from a systems perspective, it's a little bit hard. If you approach it purely from a mathematical perspective, I think you kind of miss you miss what the bottlenecks are. So you kind of need to understand both. What is the bottleneck kind of from a system perspective, and how do I change the algorithm a little bit, rewrite things mathematically to still get the same answer, but be much more hardware friendly. Yeah.
From what I understand, it was like GPUs came out, and then they were like, oh, this could be really useful for neural nets. And so it wasn't really designed for that use case or transformers. And then now you see on the news a lot of companies coming out creating AI specific chips. Do you know if how they're specifically changing the architecture to make this more efficient?
Yeah, so the question is, how would new companies making chips that are more tailored to AI applications? So one way we've seen, for AI applications, one characteristic is that they have a lot of kind of parallel processing. So things like matrix multiplication, which is quite different from graphics workload. So as a result, when these machine learning workload became popular, for example, Google came out with TPU, and what they did was they just put in specialized units that do matrix multiplication really fast. And these things are called systolic arrays. You can read about them. So TPUs came out in 2015, and they have these systolic arrays that only accelerate, that's specialized to accelerating matrix multiplication. And of course, NVIDIA had to respond, so they put tensor cores, which is also systolic array in their V100. So the shift has been, let's put more specialized units that do matrix multiplication. I think back then people weren't specializing to the architecture themselves, so they were like, okay, let's specialize in matrix multiplication. There's an interesting trend where maybe more recently people feel that, okay, maybe the transformer architecture has been dominant for 6 years. Maybe we want to specialize to the transformer architecture. And we've seen a little bit of that. It's kind of a risky bet. Like, if you make chips that only work for transformer, what if someone else, something else come out? I'll mention in the second half of the talk. But is a somewhat sensible bet. And if you want to specialize your transformers, for example, NVIDIA has this thing called Transformer Engine for the H100. It's not really a hardware thing, it's more of a software thing where they do some of the operations in lower precision, FP8. And they integrate with transformer, make it easy to use for transformer. Who knows for the next chip, the B100, who knows if they're gonna, maybe put a specialized attention unit on their hardware. Like that part, I don't know. Yeah.
Yeah, so you mentioned that for your solutions, like sparsity and low run, they did reduce the flops, but really didn't decrease flop time.
Yes.
So I'm wondering, what do you think the research community is focused on this area if in reality flop was not reduced?
Yes. So I think there are different groups, like they have different motivations. So there are groups, there are folks who actually train large scale models, and they, for the most part, don't use these methods. Right. So they worry more about, okay, how do I scale it up? Yeah, make sure it's scalable. How do I communicate between different GPUs and then things like that. So these are folks dealing with large scale training, and there are folks focusing on the algorithm, and they're interested in some sense, fundamental problem, like how should things scale? Things should scale linearly instead of quadratically, something like that, right? So there is more of a academic question of like, they're not so much concerned about training large scale models. They're more motivated by, hey, I write this cool paper using this cool method, using this cool math, and I've certainly done that as well. But more recently, I feel like there's been a convergence of interest. So large language models being so useful everywhere that people are starting to pay more attention to, like, hey, these fancy methods, does it actually run fast? So that's something that I've been really, really happy about. So one example, I think more recently, there's a paper called HyperAttention, which does some of these sparse approximation, but they also incorporate some of the ideas from FlashAttention. Like, they do some sparse approximation, but then use FlashAttention as a core subroutine to solve a subproblem. So I think nowadays more people are caring about performance, because if you want your stuff to deploy or be useful, I think ultimately you do have to care about performance and efficiency. Yeah, so that is changing. That's a good question. Yeah.
I was going to ask, could you talk more about the difference between the architectures of TPUs versus GPUs? GPUs are sort of the only main competitor to choosing GPUs to train models these days.
Yeah, so those are the differences between GPU and TPU. I think TPU are in some sense a little bit simpler on the architecture side. GPUs are more parallel. So GPUs here I'm showing just one unit, but you can think of it as like having hundreds of these units like working in parallel. So you need to, when you program it, you kind of need to decompose the problem into parallel things that the GPUs can then handle. This is natural from a graphics point of view. The motivation for graphics is like you want to, let's say, render games or something. You have millions of pixels. You can do a lot of computations in parallel. So GPUs are much more parallel. TPUs, on the other hand, they say, let's just tackle the core problem, which is matrix multiplication. Let's just make matrix multiplication really, really fast. So their programming model, in some sense, is simpler. You don't need to worry as much about parallelism. But ultimately, I think the core of it, NVIDIA's GPUs have also been shifting to cater towards AI workload. So everyone's putting more of these matrix multiplication units in their accelerators. Yeah.
Aside from matrix multiplication, are there any other standard tricks to sort of modify algorithms to work with?
Yeah, besides matrix multiplication, are there other tricks? I think it's pretty much matrix multiplication. Matrix multiplication accounts for, I don't know, 95% of the float. the amount of floating point operations. So if you speed that up, like you're pretty much golden. There are some applications where it's not so heavy on matrix multiplication. So some of the, if you do things like physics simulation or the oil and gas where you're doing more signal processing, image processing, then things like convolution and FFT becomes more important. But so far, that hasn't been so important that they would put like specialized hardware units on it. Yeah. Okay, these are all great questions. So I'll move on just a little bit to talk about some of the approaches you can use to reduce the memory reads and write, which is the bottleneck that we have. So as Ben mentioned, some of these tricks are pretty old, and the systems folks have known about these for a while. But there are challenges to applying these tricks. Computing things by block is a very old trick. It's from, I think, 1970s when people started writing matrix multiplication. But the softmax in attention really kind of screws things up for if we want to compute things by block, because the softmax has this normalization factor that couples the entire row together. So it's hard to just compute things by block. And for the context of training models, you do need to compute the gradient. And to compute the gradient, you need these intermediate tensors, these intermediate matrices. So it sounds like you would need to store these intermediate matrices anyway to compute the gradient. So you need to store a quadratic amount of memory. And so our approaches are, in some sense, really classical. So one is tiling, which is we're going to break things up by block, but with a little bit of a twist. You need to restructure the algorithm a little bit so that you can compute things by block. You load one block from HBM to SRAM, do all the computation, and then write out the result. For the backward pass, the approach is even simpler, at least conceptually simpler, which is instead of having to store the big matrices, n-by-n matrices from the forward pass to compute gradient in the backward pass, we don't store it. We just recompute it in the backward pass. And turns out there is a way to recompute things that is even faster than storing and loading backup. So I'll go into a little bit of details there. Okay, so for the next 2 or 3 slides, so there'll be a little bit of math of how this actually works. So if you don't follow everything, that's fine. Feel free to ask questions. But in 3 slides or so, I'll hop back up and talk again in higher level. Okay, so this is the core kind of mathematical trick that make things work, at least for attention. So here I'm drawing block diagrams of how attention computation proceeds. So you have the query and the key, Q and K, and then you multiply them together. So I'm just drawing block diagrams to get the score. You get Q and K, multiply them together to get the score matrix. And then to do softmax, you exponentiate this matrix entry-wise, and then you compute the row-wise normalization constant. So you exponentiate and sum the row and to get this constant L. And then to multiply by V, what we do is we take A divided by L, that's the softmax normalization, and then multiply by V. So this is matrix multiplication. So far I haven't, I'm just rewriting things in this block diagram form. Okay, so if we want to compute things by block, what we can do is that the queries are kind of embarrassingly parallel, so you can split by query. But the keys and values, K and V, they're coupled because of this softmax normalization constant. You need to sum across the entire row. You can't just do like local computation for just a couple of columns. So that is the challenge. Okay, so let's just try to split K and V anyway and see what happens. This is our first attempt. So let's say you split K into 2 parts, K1 and K2, and similarly V into 2 parts. The goal here is, let's see if we can, what we can do if we want to do just local computation. We want to load one block from HBM to SRAM, and then let's see if we can just do local computation. So, we'll proceed as before. We haven't changed anything. We're just rewriting in 2 blocks. So you would have Q times K1 to get S1 on the left, and Q times K2 to get S2 on the right. No change so far. And then you exponentiate things to get A1 is exponential of S1, A2 is exponential of S2. No change so far. And then the trouble comes when you want to compute the normalization constant, because you need to sum across the first block and then sum with the second block. So this is coupling the two blocks together. You can't just do one block at a time. Then when you multiply with V, let's say V is split into V1 and V2, then the output is A1 divided by L. So that's the normalization constant. A1 divided by L times V1 plus A2 divided by L times V2. So here's the challenge. The softmax normalization couples the two blocks together. So you can't just do one block at a time. And then the output requires the contributions from both blocks. This is annoying, so this is kind of how the systems folks have been thinking about it, which is, okay, this is softmax, I can't really break it into blocks. So it's hard to optimize and reduce memory reads and writes. Okay, so here comes the trick. So this is our attempt, our second attempt, and the trick is softmax rescaling. Okay, so I've rewritten what we want on the top right corner. So we want this output, this normalization constant L, which is the sum of exponential of S1 and sum of exponential of S2. And then the output we want is A1 divided by L times V1 and A2 divided by L times V2. So I'll show a way to rewrite the algorithm that gets the same answer, but that will allow us to do local computation. Okay, so let's see. So I'll use blue boxes to show what's stored in HBM, and I'll show white and orange boxes to show what's computed in SRAM but not stored in HBM. So this is important. We have to control what's stored in HBM and what's not, because as I mentioned, reading and writing to HBM is what's slowing us down. Okay, so as before, we proceed. We take Q times K1 to get S1. And then we exponentiate it to get A1. So nothing has changed so far. But here's the first change, is that we're going to compute the normalization constant with respect to just the first block. This is L1, which is sum of the rows of A1. Then we multiply with V1 to get this output O1 equals A1 divided by L1 times V1. So on one hand, this is great. We are only doing local computation. We load it in a block of K, we're loading a block of V, and we're doing this local computation. We're not touching the second block at all. This is great. But on the other hand, what's not so great is that we're getting the wrong answer. We're dividing by this normalization constant L1. But what we really want is divide by the normalization constant L, which we don't have right now. We only have L1. Ideally, we want to divide by L. So we're getting the wrong denominator, but that's okay. We'll come back and fix it up. So let's move to the second block. So we'll proceed as before. We take Q times K2 to get S2. We exponentiate it to get A2. And then here, because we have L1, we can compute L2 by taking L1 and adding it to the row sum of A2. So now, if you look closely, this L2 is actually equal to L. L2 is actually the right normalization constant. Okay, so great. We now have L2 equals to L, the right normalization constant. So how to proceed? We multiply by V2 by taking O1, and then we rescale it. So previously we divide by L1, so that was the wrong normalization constant. Now we just multiply by L1 and then divide by L2. So now we're scaling by the right thing, right? And then for the second block, we just add in the contribution, A2 divided by L2 times V2. So this kind of mathematical rewriting allows us to still do local computation, but still get the right answer. And this softmax rescaling trick actually has been known to the ML community since, I think there's a paper that formally wrote it down in like 2018. So it's not a new trick either. And so this is great. This allows us to do local computation in SRAM and without having to write to HBM and get the right answer. So one caveat is softmax. There is this trick with numerical stability, which is for softmax, you need to subtract the max before exponentiation. I'm not showing it here. If you don't subtract the max, it's not numerically stable. So in practice, in actual code, we do subtract by the max, and we subtract by the local max instead of the global max. and there are ways to like still rescale to still get the right answer. So there's a little caveat about numerical stability where you have to subtract the max, and in practice, it still does work. Yeah, you have a question?
Doesn't this mean that right now you're still having like the same barrier on the output because you have to read in O1 before you can write what O2 is?
Yes. Yeah. So I think what I show should have been, yeah. So O1 we're gonna still store it in SRAM. We're not gonna write it down yet. Right. And we're gonna just in practice, you know, if you're familiar with GPUs, like we store it in register. And so we just update those register without ever writing.
Block 1 or block 2?
Yeah, it's the same worker that's processing block 1 and then moving on to block 2. Yeah, I'll talk about how to parallelize this a little bit later. Yeah, parallelism is important. Yes, we'll talk about that. Yeah, more questions? Okay, so that's a little bit of more on the details of how this actually works. The takeaway is you need to kind of rewrite things mathematically for this to work. That's why, you know, I think it took a while for people to figure this out. Okay, so kind of popping back up, how high level, what does this look like? High level, we load inputs block by block from HBM to SRAM, and then we just compute things on chip, computing and without writing to HBM, and only to the end we update the HBM by scaling. So there's a little bit of animation by Francisco Massa. He this is he leads the XFarmer team at Meta, and I think he created Torch Vision, and he's been working on this for a while as well. So there's a little bit of animation that he made where we have the queries on the left, the keys at the top, and the values and the output are on the right, and you're moving block by block kind of sequentially from left to right. So that's kind of high level how the computation proceeds. Okay, so the forward pass is, we figure out how to do the forward pass. The backward pass, reminder, the backward pass, you need to compute the gradient, and to compute the gradient, you would maybe naively need to store the attention matrices to get the gradient of the query key and value. So what do we do in the forward pass? We didn't store things in the forward pass, right? In the forward pass, we only compute S and A kind of in SRAM, and we didn't store it. So how do we compute the gradient in the backward pass? And the answer is we just recompute things. So if you store this softmax normalization constant, it's actually not so hard to recompute the intermediate matrices. And the intuition here is that computation is cheap and memory reading and writing is expensive. So here we're comparing two implementations, so a standard attention implementation and FlashAttention. And in terms of amount of compute, FlashAttention actually incurs more computation. In this case, 13% more computation. So this is like kind of going the opposite way of what some of these approximation methods do. They try to reduce the flops. In this case, we're actually increasing the flops. We do more computation in order to reduce memory reads and writes. So in this particular case, we reduce memory read and write by 9 times. And as a result, the runtime is 6 times faster in walk-up time. So this is a little bit counterintuitive. But once you kind of understand the bottlenecks, it becomes more clear. So we can speed up the backward pass even with increased amount of computation. Okay, so more benchmarks. So we benchmark this. This is about 2 to 4x faster than kind of state of the art, the optimized baseline for different sequence length for different scenarios, whether you have masking or dropout and whatnot. So this is with no approximation. The answers are exact up to numerical error. And then in terms of memory now scales linearly instead of quadratically in sequence length. So the amount of memory saving, which is I'm plotting here memory reduction, how many times, as you increase the sequence length, you save more memory. So memory is now linear in sequence length. And coming back to the motivation of training language models with longer context. Previously, we saw that when you increase the context length by 8K, from 2K to 8K, it slows down or go out of memory. But now with FlashAttention, you can train with 8K reasonably well for example, is like 2.4x faster end-to-end on a 1B model. And for a 3B, it no longer runs out of memory. You can train it somewhat comfortably. When you train models with longer context, the models do get better. So I wouldn't go into details too much. But we've seen that FlashAttention is able to speed up transformer training, language model training by 2x and increase context length by 4x. And that leads to better models. And as you scale it to larger scale, I think this has enabled a lot of models to scale to longer sequences. For example, a lot of them happened last year. Okay, so that's the version 1 we did, I think, a year and a half ago, and then we came back and kind of optimized it further. So this is a little bit more lower level detail. So we had better parallelism and work partitioning between different warps in the GPUs. That's a little more hardware details. We reduced the amount of non-matmul flops. So again, it comes back to the intuition of the reality that there are specialized units that do matrix multiplication. So anything else that's not matrix multiplication is relatively slow. So you want to spend most of your time doing matrix multiplication. And you want to reduce communication between parallel workers. So as a result, FlashAttention 2 is about generally 2x faster than what FlashAttention 1. And I think FlashAttention 1 is in PyTorch 2.0 or 2.1, and FlashAttention 2 is going to be in PyTorch 2.2, which is going to be released, I think, end of this month. And it's also been in Hugging Face Transformer for a while. Okay, so that was for transformer training. But nowadays, a lot of the workload is in transformer inference. And I'll show some of the ideas how we can optimize for inference, and it involves parallelism. So this is joint work with the folks at Meta, the XFormer team. Yeah.
Just giving you a 20-minute warning for the inputs.
Okay. Yeah, thanks. So for inference, turns out the bottleneck, again, is in IO reads and writes, but it's about loading the KV cache. If you're familiar with transformer inference, there's this KV cache. You store the history, the query and the key. The key and the value. But the new query, there's only one new query. So yeah, you store the entire history, and then there is this, you predict one more token, and then for the next step, you kind of compare that one token with the history. So the query is actually very short, but the key and the value could be potentially very long. And the challenge here is how to load the KV cache as fast as possible. So previous method, as I show you, there is a sequential dependency. We process one block at a time. We move from one block of key and value and move to the next block, then move to the next block, and then move to the next block to compute the output. So this is fine if the query is very long, because you still have a lot of parallel work to do. But for transformer inference or generation, the query is usually very short. It's like one token or a couple tokens. So there's not enough parallelism. Most of the time, most of the GPU is just sitting idle because there's this sequential dependency. So with the folks from Meta, so we have this better algorithm for decoding. We call it flash decoding. So what you do is you want more parallelism. So again, using the same trick, we're going to load KV cache using parallel workers. And then we're going to compute this local output, just as before. And then we're going to have a separate step that will combine the local output into the final output. Again, using the same softmax rescaling trick. But this time being more aware of the parallelism on GPUs. So this next generation, quite a bit faster, 2 to 8x faster generation on CodeLlama, where the context length is very long. So 32K up to 100K. So now a lot of these use cases, for example, you want your Copilot to understand your entire code base, to generate tokens, next tokens very, very fast while having a very long history. So attention inference becomes the bottleneck, and some of this work has gone into speeding up this core workload. So in summary, this is FlashAttention is a fast and memory efficient algorithm for exact attention. There are a couple ideas: classical tiling and recomputation. And the upshot is you can get faster training, faster inference, better models with longer sequences. This is the end of the first half of the talk. So I'll pause here to see if there are questions. Yeah.
What would you say then is the current bottleneck? Is it still memory bandwidth, or is it really that?
Yes, I think so. I've spent the last 5 months at Together AI. We've been building the inference stack, and so the bottlenecks are different for different use cases. Normally, if you're running on your desktop or laptop, we call it a small batch size regime where you're serving like one user, and there. The bottleneck is loading the weight matrices, not even attention, but loading the weight matrices from the HBM to compute units. So it's still memory is bottlenecked by memory. So that's why things like quantization is so widespread. People love running like 4-bit, I don't know, Llama or Mistral or whatnot on their laptops. So llama.cpp is really popular. I think there's a subreddit called Local Llama where anytime there's a like 4-bit model release, like the people get very, very happy. So their quantization reduced the amount of size of the weight matrix, and it makes it either you fit into a smaller device or you run quite a bit faster. So that's on the generation for a single batch, single user, kind of local. You're using your local machine. And then there is the kind of data center regime where, let's say you're a provider, let's say you're OpenAI, Anthropic, Google, or something, and you're using chat. You have tons of users using ChatGPT, and they all send a request. And what you do is you bash these requests together and process them at the same time. And so it depends on the regime. Sometimes you're still bottlenecked by memory reading and writing, but sometimes you are bottlenecked by computation. So as you batch. Batching, what it does is that you still need to load the weight matrix, but then instead of multiplying by a single vector, which is batch size 1, you can multiply by like 100 vectors, which is batch size 100. So in terms of loading, the weight matrix, you still need to load this approximately around the same amount. But in terms of computation, you need to perform, let's say, 100x more computation. So the balance will shift between memory and computation depends on your batch size. And lots of different use cases I won't go into, but I think I would think about that in kind of 2 regimes: small batch versus large batch. Small batch generally bottlenecked by memory computation. Large batch sometimes still memory, but sometimes it's more bottlenecked by compute. Yeah, great question. All right, so we've seen
I was curious, Trey, do you still have any love for, let's say, some of like these attention approximations or some of the kernel-based stuff that you're doing before?
Yes, great question. So I brought up these approximation methods, and I said they people don't really use them. Within the last couple of months or so, we've seen actually a resurgence of these methods, thanks to now there's more efficient implementation. So I think just last month I've seen a bunch of blog posts and code release on making linear attention or low rank attention actually go fast. And the idea is, again, you want to use things like the matrix multiplication unit. Like, how do you reformulate the algorithm so that you can use the matrix multiplication unit? So there's kind of a resurgence to these methods. And I know Michael has been working on linear attention for a while. So that's on the efficiency side. On the quality side, we've made a lot of progress on these approximation methods as well. Thanks to some of the work, for example, from Michael, that the quality now is getting close to sometimes matching the full attention. So it's quite exciting. We're making progress on both the quality and the efficiency side for these approximation methods. Yep. Okay, so for the last 10-15 minutes or so, I'll just talk about how some of these ideas will generalize to other models. So obviously Transformer is dominant, and 90-95% of people are using Transformer for these applications. But at the end of the day, Transformers still scale quadratically in sequence length. So we've reduced the memory computation, but we're actually not reducing the amount of computation. And with inference, you still need to keep around this KV cache. We have different ways to deal with that, but it's still kind of a headache. And For example, at the startup I'm in, we're building an inference stack and dealing with the KV cache is kind of, 80% of our problems are from dealing with the KV cache. So I'll talk about some other model architectures that are different, are not transformer. We've seen some progress recently where they do almost as well or as well, or maybe sometimes beating transformer on language modeling. So I'll talk about Mamba, selective state space. So this is joint work with Albert Gu, who's now a professor at CMU. He finished his PhD from Stanford last year. So a lot of the credit goes to him. Okay, so I'll just do an overview of what these model architectures look like. So the core computation, the core layer, is going to be a state space SSM. So similar to things like CNN, where the core layer is convolution, you wrap it around normalization and linear layers and residual and so on. You get a CNN architecture. For the transformer, you have the attention layer, and then you wrap around kind of the same thing, and you get the transformer architecture. So similarly, with state space, you have the state space model, SSM, and then you wrap around kind of the same building blocks, and then you get a state space neural network, SSNN. So I'll focus mostly on the SSM side, and I'll just touch on the architecture a little bit. So the architecture stayed largely the same, which is kind of swapping out the core layer. So things like layer norm, residual still stay the same. Okay, so recurrent neural network, they were pretty popular from back in 2015, 2016 or so. They were state of the art. They were used for translation. I think some of the text-to-speech model running on phones are still using a recurrent neural network before Transformer came out. So Transformer came out in 2017, and kind of a lot of people, or most people, switch over from RNNs. But RNN is still great in some sense. They're natural at modeling this kind of sequential process, because what they do is they're recurrent. So they kind of summarize the history into a hidden state, and then given that hidden state, you can generate the next token. They're good for inference, but they're not great for training. So they're not friendly to accelerators because they have this sequential dependency. Also on the quality side, it's harder to optimize for them because it's harder to optimize because they have vanishing gradient problems. You can read more about that if you're interested. And so attention or transformer came out, and they have this dense interaction where all elements interact with each other kind of pairwise. So they perform really well in language. They're parallelizable. But the downside, as I mentioned, is that they have quadratic TAM scaling in terms of during training, and during inference to generate a new token, you kind of have to keep around the entire history. So one step of inference scales linearly in the sequence length. I'd like flash decoding to make that fast, but fundamentally, should things still scale quadratically in sequence length? And selective state space, this work with Albert, is our attempt to get the best of both worlds. So on the efficiency side, we would still have parallelizable training and fast inference. And on the performance, on the quality side, we've seen, at least at the smaller scale, we're able to match transformer on language models. So we're matching at the 3B scale. And with long contexts, we can improve, the model continue to improve at up to million length sequences. Okay, so just a little bit of overview on how state space work. They're actually very classical. They are from the 1960s. For example, if you heard of Kalman filter in signal processing, that's the work that kind of pioneered state space models. And they're mathematically quite elegant. They're defined by two very simple equations. So you have the input x and the hidden state h and the output y. And so the h is defined by a differential equation where h is varying by some factor that's controlled by the current h and then the input x. And then the output is, in some sense, just a projection of the hidden state h. So they've been there since the 60s. They haven't really worked well for deep learning, but Albert and Curran and Chris Ray with the S4 paper, they show that they can work pretty well, really well for for deep learning for some of the applications. So they figure out a way to put them in a deep learning architecture. So using state space as a core layer, and then putting things like layer norm and linear layer and residual together to make an architecture S4 that work really well, especially for things like audio and images. So they have a bunch of advantages. So they have a continuous representation, so they're great for like continuous domain like audio. They have a recurrent representation, so they connect to RNNs. But they also have a convolutional representation that allows fast training. So I won't go into details. The idea is still you're using these very simple primitive, defined by these two equations. But if you figure out a way to run them efficiently during training, run them efficiently during inference, and kind of put all the building blocks of modern deep learning in them, you get an architecture that performs reasonably well. So I won't go into details. But I want to highlight one work, which is, on the system side, how do we make them fast? And turns out they're equivalent to long convolutions. So it's equivalent to convolving with a very long filter. And I want to, so the way you do that is on any accelerator, you want to do the Fourier transform. In order to do long convolution, you do a Fourier transform, pointwise multiplication, and then an inverse Fourier transform. So I think that's called the convolution theorem in signal processing and in signal processing. This is pretty classical, but turns out there's no fast, or you can make convolution quite a bit faster, even faster than cuFFT, which is this vendor library from NVIDIA. And so I just want to highlight some of the work done by Dan Fu and Herman. Maybe Dan will one day give a talk at this seminar where about taking this kind of hardware-aware thinking from FlashAttention. Dan and I collaborated on FlashAttention. He took some of this thinking on FlashAttention and applied to the problem of speeding up convolution. And for example, on cuFFT, you get the utilization of the hardware around 2%, because again, it's very much dominated by memory reads and writes. And Dan and Herman use some of these the same ideas from FlashAttention, and they made FlashFFT conv. And the utilization is like way higher, and it's close to FlashAttention. So I just want to highlight the excellent work from these folks that using the same ideas to show that some of these ideas are actually general. They don't just apply to attention; they also apply to convolution. So I'll skip some of this, so the main feature of state space is that during training, you use this convolution mode. During inference, you switch to this recurrent mode. They're equivalent. They compute the same thing, but convolution is great for training. You can use, for example, some of the work that Dan has done, making convolution really fast. But during inference, you're generating one token at a time. You use this recurrent mode. So with Mamba, we're kind of changing that a little bit. So the issue with state space is that they don't work super well for language. At least so far. I've personally have worked on this as well, and they haven't been able to match kind of the strongest transformer until more recently. The motivation here is that you can understand the quality in terms of how much of the history is being summarized, right? The state space or RNNs, they kind of summarize the entire history into a fixed context length, a fixed state vector. So this is efficient. This is great because given this fixed size state vector, you can generate the next tokens because you kind of have summarized the entire history already. But they generally don't do well on information dense modalities like language. On the other hand, attention, another way to view it, why it performs so well is that it actually keeps around the entire history. So it's very easy to kind of look back what happened in the sequence, what happened in the document, 2000 time steps before. So it's great for performance, but at the same time, it's inefficient because you need to keep around this history. For training, this is the cost of the quadratic scaling. For inference, is the cost for having to keep around this KV cache. So we want we want to use, get the best of both worlds. And this is the selection mechanism in Mamba is one way to get there. So the idea is that we want the model to still summarize the history into a fixed state vector, but we want it to be smarter about what to put in the history. So the idea is the model is able to kind of pick what to put in the history based on the input it sees. And the core idea is actually very, very simple. So with S4 and so on, you have these ABCD matrices that control the dynamics. I won't go into details too much. With Mamba, with S4, these are parameters. They don't depend on inputs. They're parameters of the network. With Mamba, what we do is we just say, hey, let the model control how much to put in the history. And that means that you let these ABCD matrices depend on input. They're functions of inputs. And just this simple change actually allow the model to do very well on language modeling. On the efficiency side, once you have ABCD depending on input, you can no longer use convolution. So, for example, the excellent work that Dan has done, we can no longer use his kernel. So we have to find some other tricks to do this. And it's the same trick actually, which is we're going to keep this large hidden state in SRAM and we never write it down. We only load in the input and we only expand in the large hidden state in SRAM. So again, using kind of the same memory hierarchy idea, you can still do this recurrent mode really fast without having to write out this big hidden state. So that again, kind of the same idea shows up. So I'll just show you some of the results. So we did scaling law analysis comparing transformer. This is kind of vanilla transformer that was used in GPT-3 with some of the kind of transformer free models like H3 and Hyena and RWKV and RedNet. And compared to Transformer++, which is kind of the strongest transformer architecture that we know of based on the Llama model and training recipe. And we compare it to Mamba. And Mamba here is the purple curve. So the x-axis, the flops, how much computation you perform, and the y-axis is perplexity. So lower is better. And so we see Mamba here scaling, about as well as Transformer++, sometimes beating Transformer++. So this is really exciting to us. This is Mamba is kind of the first attention-free model to compete with strong modern transformer models. So this is very exciting. We also train models up to 3B and compare to some of the models out there like Pythia and so on, OPT, and Mamba is matching or beating transformers of similar size. So we're very excited about it. Maybe finally we have a non-transform architecture that does really well on language modeling. Of course, there's still, the caveat is it's still validated at relatively small scale at 3B, and there's still a lot of open questions about, how to do inference efficiently with these state space models, and whether they can follow instruction or whether you can quantize them efficiently and run on device and so on. So there's just lots of open questions still, but this is something I'm very excited about. So I will stop here. I think we're at time. So the takeaway message is that as you think about both the algorithm on the model side and the hardware, I think if you think about both of them, that kind of gives you superpower. You can speed things up. You can devise new architecture that runs really well, and you can unlock a bunch of capabilities. So I think excellent choice you guys have made to attend this, to enroll in this seminar. I think you see more of these ideas coming up, and they're becoming more and more relevant to kind of modern AI. So with that, I'd like to thank you for your attention, and I'll stick around and answer questions.
Let me turn off the stream.